And we're recording. Okay, so picking up where we left off. Last time we were talking about Gauss's divergence theorem, the divergence theorem, Gauss's theorem, whatever you want to call it. And we saw some physics applications, and that made for a nice breaking point. Now we're starting with a new but similar theorem, right? And so, again, I know y'all have noticed the pattern. We keep seeing theorems where, we look at a new context, we make a definition of what we mean by boundary, including talking about orientation. Then we talk about the accumulation feature associated to some specific quantity that we can define. And then we make the observation, well, that means that we can talk about where in the interior stuff actually happens. We measure it on the boundary, but it's actually happening in the interior. We define a corresponding notion of a density appropriate to whatever we're computing, and put it all together, and lo and behold, we've got ourselves a new theorem, right? Now, I just swiped through that super quickly. Obviously, we're going to go back and talk about it in more detail, but I want to point out it follows the same pattern, right? So just a reminder, Green's theorem, define boundary, worry about orientations, make the observation about accumulation, right? Usually from canceling interior terms. Talk about locations. Observe that there's an associated density and put together the theorem, right? It's the same exact pattern. So keeping that in mind, let's now dive into the details. What we're going to consider now is still in R3, right? Just like the divergence theorem, this has us in R3 again. The difference, one of the big differences, however, is that we're going to be looking not at solids in R3, but we're going to be looking at surfaces in R3. Now, that's dimensionally lower, right? It's not a three-dimensional solid thing. It's a two-dimensional surface, type thing. Okay. All right. So we need to, again, step one, define what do we mean by boundary. Now, without worrying about orientations, boundary is a pretty simple idea. Boundary is where the edge is, right? I like to think of it as if you have a surface, and if you have an ant walking around on the surface, then the ant, ants don't have any noticeable mass to speak of, right? And they have, sticky fingers or something. They walk upside down, etc. They can go anywhere they want, and they don't really notice anything interesting happening until they get over to here, at which point they're like, wait, where's what, there's nothing over there, what do I do, right? So boundary is where the ant gets confused. I think it's a nice simple way to think about it. Okay. But there remains the question of orientation. So what is the correct orientation? We've got this curve here. We agree that this curve is the boundary, but which way does it go? Okay, so there is a rule to this. As with all of the previous rules that we've seen about orientations, yes, it's arbitrary. But it's two things. First of all, it needs to dovetail with things that we've already talked about. And the choice that I'm going to give you here will dovetail accordingly. And it also, arbitrary though it is, everyone's gotten on board with one particular choice, and so we're going to, so that we can speak the same language as the rest of planet Earth, we're going to make the same choice. So arbitrary, but not optional. All right, so here it is. Here's the deal. If you have a surface, here's your surface. Specifically, if you have an oriented surface, and it does need to be an oriented surface because we're going to eventually be talking about fluxes that's going to come up, so we need this to be oriented. So there is a normal vector defining the orientation, which way is the correct direction through that surface. Given your oriented surface, here's what you do. Right hand, thumb, point the thumb in the direction that the orientation of the surface points. Right? No, now again, right hand, very important that it be your right hand. Notice that your fingers want to bend a certain way. Yes, you can do hand yoga, let's not. So your fingers of your right hand want to curl around your thumb in a certain direction, right? And I'm going to say that your fingers then define what I like to call a swirl. There's two possible ways that you could swirl around that that normal vector, you could kind of swirl this way, or you could swirl the other way. So the fingers of the right hand define which of those two possible swirls on the surface is the correct swirl. And then what we want to know to define the orientation on the boundary is to see how does that swirl sideswipe up against the boundary. And in particular, in this case, it's if you were to take this picture with the swirl, and if you were to sort of move closer and closer to the surface, that swirl would brush up against that boundary curve in a well-defined direction. And that's what we mean by boundary of S. The boundary of the surface is oriented as indicated by that side swipe. Everybody see the deal? It's a little bit weird. It's one of our weirdest choices, right? I mean, but nevertheless, that's the deal. Yes.
So, are we always picking the outward normal vector?
Nope.
Okay.
Nope. So the point is, the surface has to come with an orientation, right? And a great question. A lot of students tend to think that up is by definition the good one, and that down is by definition the bad one. There's no such thing, right? An orientation, a surface can be oriented whatever way. And in this case, I drew it up, but that was arbitrary. Yeah. Is that satisfying to everybody? All right. Okay, so that's what we mean by a boundary. All right, let's talk accumulation. I need to tell you... Oh, sorry, go ahead.
How does that fit in, like what you just said, with how the boundary is oriented away from the solid? Isn't it always defined when oriented surface solid?
I guess I don't quite understand the question. Say again.
Going back to Gauss's theorem, we define our boundary as, or like our orientation.
Yes.
Away from the solid.
Away from the solid.
Isn't it always, or like it would always be away from the solid, or no?
Well, so this is an apples and oranges thing. So if you have a solid and you're talking about the boundary surface, right? So the solid is a three-dimensional, like a rock, right? Well, the surface is like this, and then the orientation outward, away from the solid, right? But notice that could be either up or down, depending on where on the boundary of your rock you're talking about, right? So this is just a different deal. In this picture, there is no solid, right? My surface might be the boundary of a solid, but it might be a piece of paper just sitting up here in space. Okay. In which case, there's no solid, and so there's just kind of no such issue. Yeah, cool. Good. All right. So let's talk about accumulation. I've got to tell you what the quantity is. There is an accumulating quantity of interest. I suppose also an arbitrary choice. Why are we thinking about boundary circulation here as opposed to any of a number of other things that I could be interested in computing? And the answer is because this, we will momentarily see, is an accumulating quantity. It's because it's an accumulating quantity that we care about it. So it's not that we were intrinsically interested in boundary circulation first, necessarily. So this is this is a choice that we make because this leads to a cool theorem. Okay. So I claim boundary circulation accumulates. Here's the picture. I guess I'll walk through the picture first. Before I do that though, let me dial it back. I'm going to come back to Green's theorem and remind you of this picture, right, where we were interested in boundary circulation again. And the idea was that if you look at the hull, its boundary circulation is computed by those two line integrals. Right? If you look at the left side, the boundary circulation is these two integrals. And then if you look at the right side, right, then the boundary circulation is those two integrals. Punchline, we ended up with this kind of extra and this kind of extra. And we observed that, but those are integrals that are on the same shared edge, just going opposite directions. Those line integrals are negatives of each other and they cancel in the summation, and it's like they weren't even there. Right? So with that as a reminder, a shockingly similar thing happens looking at, now again, boundary circulation again. right? On surfaces this time. And so let me walk through the whole thing again. So here's the whole surface, and I can talk about the boundary circulation. Now, we got to worry about orientations. You got to think about as I have it drawn here, the normal vector is like that, and the fingers and the swirl, etc. And the resulting boundary orientation is like that. Right? Is everybody comfortable with that? Thumb, swirls, etc. Okay. So there's the whole. There's our allegedly accumulating quantity associated to the whole surface. And then I look at the left side. Boundary circulation. Boundary circulation is that plus that plus that plus that. And then I look at the right side. Boundary circulation is that plus that plus that plus that. And altogether then, we notice that just like in the greens case, that shared edge in the middle, well, it appears twice. It's part of the boundary of S1. It's part of the boundary of S2. With opposite orientations because of this whole business with the way we orient boundaries of oriented surfaces. They get opposite orientations on this shared edge and they cancel. So the total of green plus blue is really this, which you notice again is the boundary circulation around the hole. That make sense? I mean, it's morally identical to what we saw with Green's theorem. It's just, instead of being a two-dimensional thing living in 2 dimensions, this is a 2-dimensional thing living in 3 dimensions. Okay. All right. Oh, whoops. But I just hit the wrong button. Okay. All right. Here we go. And I'm on the wrong thing. Here we go. Okay. Again, just like with Green's theorem, we've seen that when you do a slice through the middle of a surface, you get a shared edge which appears twice as boundaries of pieces, but with opposite orientations, and they cancel. And you can see that same thing happening on all these shared edges, like that little shared edge right there. Right? Well, it's oriented that way as part of the boundary of the left side. It is oriented that way as part of the boundary of the right side. Cancels. And likewise, all these interior pieces. So slice and dice as much as you like. It makes no difference at all. And then I want to make the additional point, though, that if I look at the whole, if I look at this boundary circulation of the whole surface, and if I ask, okay, this boundary circulation, where does it happen? And, y'all heard me say this a million times, and I'd say I'm going to say it a million more times, but we're getting near the end. But a very important point is that even though we measure it on the boundary, it's actually, you can very reasonably think of it as actually happening in the interior. And this, for example, this purple boundary circulation on the whole, well, you can think, I better switch to pencil mode, you can think of that as being that boundary circulation plus that boundary circulation plus, et cetera, right? And so I can literally talk about, how much of this purple circulation is happening, let's say in this green piece here. How much is happening there in that green piece? Again, we see it on the boundary, but I claim that we can view it as happening in the interior. And the amount that's happening in the interior is just, whatever that circulation is around the boundary of that piece in that location in the interior. Okay? So same idea. So this quantity in question, this accumulating quantity, is, you think of it as being distributed across the interior, kind of like a stuff. It's think of it as being a physical stuff because it behaves like a physical stuff, at least in this sense. Okay. Okay, and as such, if it's a stuff, it behaves like stuff, I can talk about its density. And so again, our object in question is circulation. If you want to talk about circulation density, then we talk about circulation per unit area, because that's the interior over which it's accumulating. Right? So circulation per unit area. And it's a concept that we can ask about and we can compute. And just like I had with all of our other theorems, when we get to this point, yes, there are some detailed calculations that you can go through to compute what this circulation density is as a formula. It's, I think, not as important as understanding what that resulting formula means and how to interpret it as, again, viewing it as circulation density, I think is a big deal. This is something that's conceptually meaningful. How to compute the formula, whatever. But here it is, circulation density, and the formula is this. And you're not responsible for knowing where that formula comes from computationally. Okay, now before we go on and celebrate and write the theorem, spike the football, I do want to acknowledge there is something weird about this. If you look back at Green's theorem and Green's operator, in other words, our circulation density here in the two-dimensional version, it's a formula that you'll notice it depends only on the vector field F. It depends only on what you might call not the surface. It doesn't have anything to do with the surface. Green's operator, you can compute it for any vector field no matter what region or curve you might eventually be interested in, independent of the domain. And that's what's peculiarly not the case here. So this is an eyebrow raiser. It does depend on the vector field, but weirdly, it also depends on, the orientation, which comes from the surface. So that's strange, right? This is not the case in Green's theorem. It's not the case with the divergence theorem. Right? The divergence theorem, the density is divergence. It depends only on the vector field. It's not the case with the fundamental theorem of calculus. With the fundamental theorem of calculus, the change density is the derivative, which is completely independent of what interval you're looking at, right? So this thing where all of a sudden this density depends on the nature of the domain is different and weird, and I'm going to have to talk about that a little bit later today. So anyway, I just kind of wanted to point that out, a little bit of foreshadowing, and we'll dive into what that means and why that is actually natural in a couple of minutes. But anyway, we have our circulation density. There it is. So here's our theorem then. We view circulation as being a quantity. That's old news. We talked about that a long time ago. You can view this as this is the same exact quantity of interest as in Green's theorem, just a different context, three-dimensional instead of two. We've made the observation that it's an accumulating quantity, so the whole is the sum of the parts. And then I can ask, all right, well, what is the associated density? And that's what I wrote down on the previous page. The density is curl dot unit normal vector. Write that down. And you could stop right here and say, hey, okay, cool, theorem, right? That's Stokes's curl theorem, and that's fine. You could totally do that. But as y'all may recall, I like grouping all of this together because if you think about it, this thing right here, the ds scalar is telling you when you're looking at a little piece of surface, the ds scalar tells you how big that is, how much area there is in that little piece of surface. And this thing right here is telling you, if you have your little piece of surface, it's telling you what's the orientation. How does that little piece of area sit in space? Might be upside down or backwards or what have you. And that normal vector defines that orientation. So altogether, these really come from the same place. Right? The normal vector and the ds are talking about little pieces of the domain. They're telling you what you need to know about the little pieces of the domain. So let's lump them all together as the ds vector. And of course, we did this long ago when we were defining flux integrals in the first place. But and nevertheless, I think it's just, you might look at this original integral and see integrand and differential. But I prefer to view it as integrand and differential, like that. Okay, and our book uses the same notation that I do. So this is my preferred way to write Stokes' curl theorem. Then is to write it like this: circulation is an accumulating quantity, can be computed as a sum over the interior. Works out as just the way the algebra works out. It ends up being a flux. That's strange. But it's a flux through that interior surface, and it's a flux of the curl of the vector field. Okay, how we doing? Everybody following? Everybody happy? Everybody seeing all the analogies with the other previously seen theorems? Okay. All right, let's do one. Get our hands dirty. So the question. By the way, I like to start with a sort of a stand back observation about this question. Compute a line integral, vector field given, curve pre-parametrized. Notice the question does not announce itself as being a curl theorem question. It just says compute this line integral. Right? In fact, you could even view this as being a little bit of a misdirect, because I describe the curve by giving you the parameterization. It's almost like the question's kind of nudging you over toward, you pull back through the parameterization. Plug and chug, in other words, f dot x prime dt and all that. So don't fall for that. Don't fall for. Don't assume that the way the question is phrased is necessarily going to be pointing you toward the best solution method, right? But rather, just realize that when you're computing a line integral, there's several different approaches that you might take that might be the best one. Who knows? Maybe parameterize and plug and chug might be good. We're already parameterized, so all we got to do is plug and chug. There's a temptation there. I don't think it'd be a good method, though. Look how ugly our vector field is. Well, I don't want to do that. I don't think y'all do either. Okay, well now it's a line integral. Hey, maybe the fundamental theorem of line integrals would be a good way to do this, right? So maybe it's possible, based on what we know now. And so you got to entertain the possibility of that as well. Side note, I claim it's going to turn out, and we'll see. Probably not today, but probably tomorrow. Wednesday, we're going to see that actually fundamental theorem of line integrals would not apply here. And again, we'll talk about why that is next time. But our third option is, line integrals could be viewed as, something that you can compute with Stokes' curl theorem. Right? I can use Stokes' curl theorem to turn a line integral into a flux integral that might be better. Everybody with me? Okay, so you got to make that choice, and so always be on the lookout when you see questions. Compute this line integral, compute that flux integral. Get all your options identified and on the table first, and I have some methods for that as well. We'll talk about those later as well once we have all of our tools. So that'll be Wednesday as well, I think. But identify your options and then choose accordingly. Now this one, I'm going to just let you know, this is a Stokes' theorem question. By far easiest to do with Stokes' theorem. So now there is a catch with Stokes' theorem. You might even see this coming. We talked previously about Green's theorem and observed that Green's theorem does not just compute any old line integral. It very importantly, and it says so right here, only allows you to compute line integrals around boundaries. Right? Again, it says so right there. Only line integrals around boundaries. And this is not some point of formality or mathematicians being upset about rigor. Our curve has to be the boundary of a region because that region is the domain for our new integral that we're going to try to turn it into, right? So if your curve is not a boundary, it's not that you can't, that it's not equal to the corresponding double integral. It's that there is no corresponding double integral because there is no solid domain anti-boundary. And so the whole thing, it just crashes and burns severely if your curve is not a boundary. So we have the exact same deal here. Notice the exact same, let's see here. So it says so right here. If you want to compute a line integral, it's got to be a boundary of some surface. And why? Well, it has to be the boundary of some surface because that surface is the, hit the wrong one, didn't I? Look at that. That surface is the one through which we would have to compute a flux. So if our curve isn't a boundary, there is no surface to even talk about a corresponding flux integral, much less is it equal to. Right? So, very important condition. You got to keep that in mind. You can get in massive trouble. You can write stuff down that doesn't make any sense at all, but looks good. So it's kind of a landmine situation, right? And so be very, very, very careful. Always make sure to think through whether your curve is a boundary. And is our curve a boundary? But we got to think about our curve here. You'll kind of recognize the circular aspect of this parameterization, right? You see x squared plus y squared is 1 and all that. Z is equal to 0. This minus sign just kind of has you going around the other direction then. And this goes 0 to 2 pi. So sure enough, our curve is indeed a boundary. Now, do be careful. Again, you got to worry about orientations. It's a mistake to think that this curve is the boundary of, and I'm just going to fill in this disk here and just leave it at that. If I just say, oh yeah, it's the boundary of this disk, that disk, as I have it drawn, not oriented. If I just say disk, end of story. It's not an oriented thing. It does not have an oriented boundary. So we have to talk about the orientation of this disk, and geometrically, I can kind of see that this is the surface, right? But how do I know? How do I decide which of the two possible orientations to choose? I'm going to say kind of trial and error, right? There's only two possible candidates for the orientation of the surface. Just try them. So I don't know. Let's start with this one. Might that be my orientation of my surface? Well, if it were, and then you play the game, thumb in the direction of your candidate, your hopeful orientation. Think about which ways your fingers of your right hand want to go. That defines a swirl. And just notice, as you drag this swirl near the boundary, it's not going the direction it's supposed to. So this is the wrong orientation. Everybody with me? Process of elimination, it's got to be the other one. But let's, nevertheless, let's be careful. Oh, I'm never going to be able to erase that without, oh gosh. There we go. Okay, so let's try the other one now. Let's try this as a candidate orientation for our anti-boundary surface, 0, 0, negative 1. Okay, is that correct orientation? Well, right hand, thumb in the direction of the orientation, or our candidate orientation. That would have, notice what my fingers are doing here. Because my thumb is pointing down, I have to sort of turn my hand like this. That has my right hand fingers swirling that way, which does sideswipe in the correct direction. So this is the correct anti-boundary orientation. How are we doing? Is everybody happy? Is everybody with me? Okay. All right, so you just got to play that game. You just got to look at your, always keeping in mind what orientation is given on your curve. This curve has an implied orientation based on the parameterization itself. The direction the parameterization itself goes tells you the orientation of the curve. And then you gotta just consider the candidates. One of them's going to be wrong, and one of them's going to be right. Okay, so we're in business. We've got a perfectly good anti-boundary surface, and then it's all over. But the shouting, pretty much. Let's see. Let me get back into highlighter mode. My curve is the boundary of a surface. Boundary circulations, according to Stokes' curl theorem, are fluxes of the curl of the original vector field. There's Stokes' theorem. And now we just have to compute this integral. It won't always work out to be nicer, by the way. Sometimes, if you have a, not particularly desirable integral, sometimes this will be even worse, right? Could be, right? So there's this is not a magic wand. This is just it's something to try. And, sometimes it'll help, sometimes it won't. In this case, it actually works out really nicely. This is a great, convenient little integral to compute, and I did this on purpose, but the curl works out to be just 002. Let's see here, where's my vector field? Here it is. This vector field here, y'all know how to compute curl, various partial derivatives, kind of a sort of a fake determinant, right? Symbolic determinant to compute. And you punch it out, and it ends up being just 002. It's constant. Well, that's nice. You got lucky, right? The normal vector we've already discussed. That normal vector is 0, 0, negative 1. And so constants everywhere. Just love how this is working out. Our entire integrand is just negative 2, and that makes this a super easy integral. The surface, after all, easy surface area. So, boom, our answer is just that. Everybody okay? So we got, in this case, Stokes' theorem turned a not particularly desirable integral into a much easier integral, and that's the hope. Okay. Alrighty. Okay, so let's go back and talk about that business with the orientation, and so I'm going to first go back to the fundamental theorem of line integrals and recall that we did encounter actually a situation kind of similar to that, and I deliberately didn't make that connection when we were talking about how we've never seen this before, right? It doesn't come up in Gauss or Green or what have you. But it did come up in the fundamental theorem of line integrals, right? Our density, if you look at quantity and how that relates to size, our density was gradient dot T. And you can flip back through the notes to the chapter 6 notes, whatever section this is, 6.3, I think it was. And you'll remind yourself that our scalar notion of density is gradient dot T. So again, it's this weird circumstance where our density kind of depends. It depends on your external function. Yeah, sure, but it also depends on how is your curve oriented. Right? It depends on both in this kind of weird way. And so then I decided to rewrite it. I'm going to rewrite by taking the size, that of course is part of the piece of curve, it's part of the domain. The orientation, of course, also part of the domain. That's defined by the domain. And I said, well, I tell you what, let's combine these together, right, and view that as a single vector, you might think of this as kind of a vector size. In some sense. And viewing that as a vector size, and if you ask yourself, well, what's the relationship between quantity and not a scalar notion of size, but between quantity and a vector notion of size, then you see how the algebra works out. It's just this thing, which I then call an oriented density, because we have an oriented notion of size, the way the algebra works out, we are then left with a vector, namely an oriented notion of what do you multiply by oriented size to get oriented quantity, to get quantity. So natural to call this an oriented change density. So I hope that rings bells. I hope you all may remember that discussion from back then. So in fact, we're going to do something very similar in our new situation. I do want to flesh this out a little bit more, though, real quick, and observe that this oriented change density, well, it's the gradient. It's something we've studied pretty extensively back in chapter 2, I guess it was. And so let's just take a moment to recognize what do we know about this oriented change density, aka gradient. And well, we know that being as it is a vector, of course, if as being a vector, it has a magnitude and a direction, and each of those means something. And again, thank you, chapter 2, right? This is all flashbacks to chapter 2. The magnitude of the vector is telling you, honestly, how much is the function changing? How fast is this function changing, independent of our, what direction I'm going, right? Let me say it differently. The magnitude of the gradient is telling you how steep is this hill that we're walking around on. And how steep the hill is, well, of course I mean how steep in the uphill direction. Nothing is steep if you're doing a traverse, right? So let's take my personal experience out of the consideration. The hill itself, how steep is the hill, magnitude of the gradient. Right. But now our gradient vector also tells us something else. It tells us what direction is that increase happening. It tells us which direction is uphill. It tells us which is the direction of fastest increase, whatever you want to call it. So, independent of what we're doing, independent of whether we're actually walking uphill or maybe we're walking a traverse or maybe we're walking downhill, who knows? Independent of that, hill only, how steep and in what direction? Okay, so that's our interpretation of oriented change density. All right, now let's take all these ideas and try to apply very similarly in the Stokes context. So we've already done some of this. I've already written this down. I've already grouped these together. And notice that puts us in this exact same situation, whereas if we look at accumulating quantity, now circulation per unit size, if you take a scalar notion of size, then you get a scalar density. And this was our first circulation density that we talked about. It's a curl.n, and it's weird because it's got part of the domain is in there, and it's just kind of a weird way a weird conclusion to have. So again, just like we did here, where we had a scalar that had a dot product in it as our density, I'm going to, again, kind of group all of the domain stuff together. Right, so I'm going to group all this domain stuff together. Here we have the size of the piece of surface, the orientation, the direction that piece of surface is normal vector is pointing. And then, having done so, notice I have kind of an oriented size, just like up here, dx is our oriented size. And in the same way, then, that gradient, we interpret that as a leftover as being oriented change density. It's what you dot with the oriented size to get quantity. Likewise, here, we have curl is our oriented circulation density. This is what you dot with our oriented size to get quantity. This time circulation instead of change. What do you think? Is that all right? It's kind of a choice of a point of view, and again, it has some nice advantages. Now, what I'm about to tell you about curl, is not what we've seen before. I haven't broken down curl particularly, and I'm not going to prove, by the way, the claims that I'm going to make here. I'm just going to I'm going to make some assertions, and I'm going to draw some pictures that show it in action and that show it being plausible, and I'm going to leave it at that. So this is going to be plausibility argument only. But in the same way that gradient has a magnitude and a direction, both of which mean something, that tell you important things about how the hill steepness is. It's telling you about the steepness of the hill in its different ways, right? How steep and in what direction. Likewise, curl breaks down as a magnitude and a direction that tell you something. It tells you something about how the vector field is circulating. In particular, the magnitude tells you, in some sense, how much of a tornado have you got here? How much is the vector field actually? I mean, is there a lot of circulation of the vector field happening, or is it kind of a gentle, not that much circulation at all? Kind of a thing, right? So, in some sense, in an absolute sense, independent of your surface, just looking, I'm interested in the tornado itself. I'm not interested in how we experience the tornado. Just the tornado itself. How strong of a tornado is it? Is the magnitude, and the vector is telling you in what direction is that tornado happening. Right? It's telling you around what axis is this tornado circulating. So here's the picture. Given a curl, again, there's two things that we can talk about. There is the, what is this axis? What is this axis around which the fluid is circulating? How is our tornado oriented? Is it a sideways tornado, right? Or is it a vertical, more typical tornado? And of course, now that comes in the form of the direction that the curl is pointing, and you can think of that as being a unit vector that defines this axis. And then it also tells you, by way of its magnitude, how long the curl vector is. It tells you how much of a tornado do we have. Okay, how we doing? I'm going to pause here. I'm throwing a lot of geometrically confusing pictures at y'all. I want to make sure everybody's happy. Okay. All right. So, my next thing here is to try to persuade you that this is plausible, that this formula that curl.n could possibly reasonably be the right answer. Again, this isn't going to prove anything, but this is just let's just make sure that this tracks with some easy examples. And so here I have two examples here. This is two separate pictures. So in fact, let me draw a line right there. Just keep them separate. And you will notice that in these two separate pictures, I've got the same vector field with, therefore, of course, the same curl. And I'm just considering two different surfaces that interact with that vector field. So same vector field. And let's think now about, in this first case, suppose I have a little piece of surface like this, oriented like so. And with a piece of surface like that, oriented like so, I can talk about its boundary. And of course, its boundary is like that. And again, you've got to use the right hand rule, thumb in the direction of the normal vector. That creates swirls. Think about how those swirls side swipe. And there's our boundary orientation. How are we doing? Is everybody with me so far? Okay, so, all right. In this case, do we have... we can see there's a tornado happening. How are we actually picking that up, though, on this boundary? Are we going to measure significant actual circulation along this boundary? And I say, yeah, absolutely. I mean, look, the vector field is going the same direction the curve is, right? So we would expect there to be a lot of circulation around the boundary there because, well, the fluid is flowing the same direction that the boundary kind of goes around. So yeah, lots of circulation. And notice that tracks with the fact that the curl and the normal vector are pointing in the same direction-ish, at least. Right? And so, you know, the claim was that this dot, the blue dot product here, curl dot in, was a measure of how much circulation you're getting, right? That's a measure of circulation density. And I claim that that's consistent with this picture. When the circulations are going kind of the same way, those two vectors that we dot also go in kind of the same way. Okay. And then notice in this next example, it's sort of the opposite. In this next example, if you ask, well, you know, how much circulation, I'm getting ahead of myself. First, let's recognize different surface. Different piece of surface there, right? I've kind of taken our surface and kind of rotated it around, oriented differently, and boundary now going this way, like that. So, step one, let's talk about circulation. Are we seeing a lot of circulation in this second example? No, we're really not. The fluid is going around that way, and that's just everywhere kind of orthogonal to the way that the surface is going. So it's like, let's see here. The fluid is doing kind of like this, right? There's this fluid circulating around that way, but our curve is like this. Right? So, you take, for example, over at, let's look at this point right here. Well, the curve is going that way. Now, the fluid is going that way. So, if you compute the line integral, you're just not getting anything along in here. The fluid is not circulating in the direction that the boundary is. So we would expect, I'm going to say, low, if any, circulation around that boundary. Does that make sense to everybody so far? And now let's think about how does our formula pick up on that? Well, it picks up on it very nicely, actually. Our curl is like that. Our normal vector is like that. Whoops, I'm sorry, there we go. Okay, so our curl is this way, our normal vector is that way, and again, those are not pointing in the same direction even to any extent. They're pointing literally perpendicular to each other, right? So, not having circulation tracks perfectly, again, in this case, with these vectors being orthogonal to each other. So this doesn't prove anything again, but I think this is this offers the opportunity to find a little bit of satisfaction, perhaps, in the idea that that this expression, the dot product, this dot product here, would be a measure of the circulations that we're seeing in these two cases, and I think this is believable, plausible, geometrically plausible. How we doing? Questions? All right. Okay. I have 1 minute. I'll almost certainly repeat this then on Wednesday because I don't think I can get very far through this, but I do want to point out there's an easy physical interpretation, and it's totally a ripoff of what Green's operator told us when we were talking about fluids. And recall that we were entertaining the idea of a fluid moving along, and in a way like this, where the velocity is greater, lower in the picture, and higher in the picture. And imagine that this is the surface of a river, and this is a little leaf that's floating on that river. What's going to happen to this? Well, the water is pushing it harder on the bottom, and it's not pushing it very hard at all on the top. And so it's going to develop a sort of a spin to it, right? This leaf is going to be twisting, rotating as it moves along. I mean, the vector field itself will tell you how fast the leaf is going to move. Yeah, the leaf does what the water does. The water, velocity of the water is the definition of the vector field. So yeah, the vector field tells you how fast the leaf is moving, but the spinning of the leaf comes from Green's operator. And again, so old news. So a very similar way, if you have maybe not water, but let's say air kind of rotating around like that, and if you had not a leaf, but a floating balloon, let's say a perfectly balanced, like right after the party, the balloons are up on the ceiling, but after a couple of days, they lose some helium, and at some point they're perfectly balanced. And they will just float around kind of arbitrarily, and the gravity is not pulling them down, and buoyancy is not pulling them up. They're just perfectly weighted. Right? Imagine balloons like that. Well, if there is a rotational aspect to the movement of the air, if the air is rotating, then the balloons, you would think, would kind of rotate along with the air in the same way that leaves rotate along with the water. Right? And so curl is going to tell you exactly how that works. And again, curl tells you two things. It tells you how much of a rotation there will be, and it tells you around what axis that rotation will be. So perfect analogy, really, with Green's operator and the two-dimensional situation. And I went over time. Sorry, I lost track. Okay, so drawing the line right there. We'll pick up here on Wednesday. Y'all have a good day. Welcome back from Thanksgiving. I hope everybody had a good break. And, see you Wednesday.